You spin up a local development environment and write a standard script to pull data from a private backend API that you control. If you execute that request through a terminal using curl, the data returns immediately. The connection is clear. But if you write the exact same request via a JavaScript fetch command in the browser, the data is quarantined before it reaches your application. You open the developer console and see a familiar error, blocked by CORS policy. When we see this error, we often assume the backend server rejected an unauthorized request to protect its data. In reality, the server likely processed your logic and successfully returned the payload. The blockade happens on the return trip. Your browser intercepted the server's response and destroyed the data before the JavaScript runtime could access it. Effectively debugging this requires recognizing that the server's job ended when it sent the response. The browser is the only entity deciding if your code is allowed to see the result. This quarantine is driven by the same origin policy, the foundational rule governing how browsers handle traffic. To the browser, an origin is defined by three components: protocol, host, and port. Imagine a React frontend on port 3000 trying to talk to an Express backend on port 5000. Because the ports differ, the browser identifies a mismatch and severs the connection. Unless two scripts share the exact same protocol, host, and port, the same origin policy forbids them from reading each other's data. The browser isolates every origin, treating external scripts as potential threats by default. This isolation exists to address a specific vulnerability in how browsers handle user sessions. Consider a user who is securely logged into their banking portal in one browser tab. In a separate tab, that same user visits a compromised website. Browsers use ambient credentials, automatically attaching saved session cookies to outgoing requests for recognized domains. If a malicious tab sends a fetch request to your bank's API, your banking session cookies are attached as the request leaves the browser. The bank server sees a request with valid cookies and returns your sensitive financial data. The browser gatekeeper intervenes here. As the data arrives, the browser recognizes the origin mismatch and destroys the payload. The same origin policy acts as a shield for your session data, preventing malicious scripts from accessing information that was never intended for them. Cross-origin resource sharing is the standardized mechanism for punching a controlled hole through this isolation. When you make a cross-origin request, the browser injects an origin header, telling the server exactly where the script is running. The server processes the request as it would any other. If the server wants to permit the read, it must attach a permission slip to the response, the access control allow origin header. When the payload returns, the browser network layer holds it in a sandbox, keeping it away from your JavaScript. The browser then compares the original origin it sent against the allow origin header provided by the server. If the headers do not align, the payload is permanently quarantined and your code receives a type error. If they match, the sandbox opens and the data resolves in your code. The server provides the permission, but the browser handles the enforcement. This explains why local proxy servers in tools like Vite effectively bypass CORS errors. Instead of calling the backend directly, the frontend sends the request to the local proxy, which then forwards it to the API. This communication is server to server. Since no browser is involved in this leg, the same origin policy never applies. The proxy then sends the data back to the frontend. Because the proxy and the client share an identical origin, the browser's security check passes. Proxies structurally bypass the browser's security sandbox, proving that CORS is strictly a browser-level construct. Because the server processes requests before the browser evaluates CORS headers, there is a significant security gap. This is particularly dangerous for state-changing operations, like post or delete requests. If a malicious site tricks a browser into sending a cross-origin delete request, the server will execute that action. The browser will block your code from reading the success message, but the data on the server is already gone. CORS restricts the reading of data, but it cannot prevent the execution of logic. Protecting the backend itself requires independent defenses, such as anti-CSRF tokens or strict same-site cookie attributes. CORS secures the user's data within the browser environment. Safeguarding the server remains the developer's responsibility through dedicated backend architectural defenses. You write a standard fetch call, hit execute, and the browser console instantly bleeds red, a CORS error. But if you check the backend logs, the server reports an HTTP 200 success. Most developers see that red text and assume the browser acted as a proactive firewall. The assumption is that the browser saw a cross-origin request, recognized it was unauthorized, and blocked it from ever leaving your machine. In reality, while the front-end script threw an error, the server actually received and processed the request perfectly. To understand why, we have to look at the same origin policy. This is the browser's baseline rule that restricts JavaScript from interacting with resources outside of its own domain. Assuming CORS acts as an outbound firewall leaves enterprise systems vulnerable. The intervention isn't a block on transmission, it's a retroactive read block on the response. Before CORS existed, the early web operated in an environment where basic HTML forms acted as open portals, transmitting data instantly across isolated boundaries. Legacy HTML form tags were historically permitted to send post requests to any domain without any security restrictions. Modern browsers are bound by an absolute architectural mandate. They cannot break backward compatibility with the early web. This creates a logic trap. If an old HTML form is allowed to send cross-origin data, modern JavaScript must be allowed to do the exact same thing. The browser handles this through the simple request, a modern fetch call that mimics the behavior of a legacy form submission. Because the browser must support this legacy behavior, it creates a deliberate bypass in modern security boundaries, changing how cross-origin execution operates. We examine the boundary between JavaScript runtime and network stack. The stack inspects outbound fetches for simple request status. First, the method must be get, head, or post. Then, headers must contain only safe-listed types. Finally, content type must be form URL end, multi-part form data, or text.plain. This is where most modern developers trip. Attaching an application/JSON content type instantly disqualifies the payload from being a simple request. If a request fits these legacy criteria, the network stack grants it special execution privileges, bypassing all proactive security checks. Let's map the sequence. JavaScript invokes fetch, passing parameters to the network stack. Because criteria are met, the stack transmits the packet over the internet to the server. The server receives the packet and executes side effects, like updating a database. Only then does the server send its HTTP response back toward the client. The critical takeaway here is that the outbound network transaction is 100% complete before the browser evaluates a single security header. The actual security intervention finally occurs at the exact microsecond the server's response hits the browser's network stack. The network stack catches the response and holds it, waiting before it resolves the pending promise in the JavaScript runtime. Now, the browser performs the explicit CORS check, scanning the response headers for the access control allow origin value. If that header is missing, or if the origin doesn't match the client, the CORS check fails. Because of that failure, the network stack proactively rejects the JavaScript promise, throwing the red error in your console. This means the JavaScript runtime is blocked from reading the response body or seeing the status code. But remember the server action. The front-end memory access is blocked, but the server's database was still updated. For simple requests, CORS is a retroactive read block protecting client memory from malicious data. It is not designed to protect the server. Consider the alternative scenario, a complex data packet hitting an impenetrable security shield that halts its momentum entirely. For modern, non-simple cross-origin calls, the browser uses the preflight request. When a request includes JSON or custom headers, the browser suspends the primary fetch request within the network stack. It sends a preliminary options ping, asking the server for permission before it ever transmits the actual data payload. If the server rejects the preflight, the browser drops the payload. The server never receives data. Only preflight requests act as the proactive firewall developers imagine. This makes the distinction between simple and preflight requests a critical architectural boundary. We have to translate these mechanics into how we design APIs and front-end architecture. A common failure is relying on CORS to prevent unauthorized state changes, like a malicious cross-origin post request meant to delete a user record. This reliance is dangerous if your backend API is configured to accept application-x-www-form-encoded data alongside JSON. A malicious site can trigger a simple request that executes the deletion on the server. The resulting CORS error in the browser simply hides the fact that the attack succeeded. The rule is that you cannot trust the client environment to protect the server's data integrity. Backend servers must always independently validate authentication and authorization, regardless of the front-end CORS configuration. CORS is designed to protect the client's memory from reading untrusted data. It is never a substitute for true server-side security. If you build web applications, you have seen this red text. A fetch request fails, the console lights up, and you are staring at a cross-origin resource sharing, or CORS, error. The immediate instinct is to assume the API endpoint is broken, misconfigured, or offline, but that is rarely the case. The target server is usually fine. That red error is actually your very own browser stepping in to prevent your code from reading the network response. To understand exactly why the browser intervenes, we have to look at the web's baseline security perimeter, the same origin policy. An origin is a specific combination of three variables: the protocol, the host, and the port. Change even one of these, like moving from HTTP to HTTPS, or requesting an API on a different subdomain, and you cross the boundary. The same origin policy exists, so a malicious script on one website cannot execute unmediated network calls, accessing private data from a different domain. But modern architecture requires crossing that boundary. Single-page applications are built to fetch data from decoupled microservices, third-party APIs, and diverse subdomains. Browser engines have to expose robust HTTP capabilities to your JavaScript, but they cannot punch holes in the same origin isolation perimeter to do it. To bridge this gap, browsers enforce a hidden architectural negotiation protocol before they ever transmit your complex payloads. Mapping out this hidden execution timeline step by step provides the technical clarity needed to debug these failures at the protocol level. Before we look at the negotiation protocol, we need to define how legacy network calls bypass it entirely. This sequence diagram maps a simple request, utilizing legacy HTTP methods like GET or POST and standard form data headers. When your JavaScript thread initiates a simple request, the data payload moves directly through the browser's network API and out to the target server. Passing through, the browser automatically stamps the packet with an origin header. Your JavaScript does not instruct this. The engine enforces it. The target server receives the payload, processes the request, and returns data, attaching an access control allow origin header to its response. Here is the catch. Your JavaScript does not get that data yet. The browser's network API stops the packet and scans that allow origin label. If the server's label matches the client's origin, the browser hands the response up to the call stack. If it doesn't match, or if the header is missing, the browser obfuscates the payload. The vulnerability here is obvious. With a simple request, the server-side data mutation happens before the browser ever validates the cross-origin permissions. That retroactive check is too dangerous for modern API architecture, so when you upgrade your fetch request with modern parameters, the browser alters its execution strategy. Setting the content type to application.json, attaching an authorization header, or using HTTP verbs like put or delete will trigger this shift. Injecting any of these parameters reclassifies the network call as a preflighted request. The moment you execute that code, the browser engine steps in and refuses to transmit your payload over the network. Your JavaScript thread is not blocked. Instead, the fetch promise is held in a pending state in the microtask queue, while the browser's network API lane locks down. The browser temporarily decouples from your application logic and takes autonomous control of the network layer. Allowing a complex, unverified mutation payload to hit a foreign server blindly is a security risk. The browser must ask for permission first. To get that permission, the browser engine generates a lightweight HTTP options probe and fires it at the target server. It leaves your actual data behind, but attaches two pieces of metadata to the probe: the access control request method and the access control request headers. The browser is explicitly asking the server, do you support these specific HTTP methods and custom headers, and do you accept them from my origin? The target server now has an architectural responsibility. It must evaluate those incoming parameters and reply with explicit opt-in headers. A properly configured server evaluates the probe and replies with access control allow methods and access control allow headers. The server transmits this permission slip back across the network, handing it to the browser engine for evaluation. This pre-flight handshake acts as a mandatory zero-trust negotiation layer between your client scripts and the foreign server they want to talk to. The browser reads the server's return headers. If the allowed methods and headers perfectly match the parameters of your pending request, the check passes. The network API unpauses, the padlock opens, and the browser finally transmits your original, complex fetch payload. Once the server processes that actual payload and returns the final response, the pending promise in your microtask queue resolves, handing the data back to your JavaScript. But consider the failure condition. If the server omits the required headers or rejects the origin during the options probe, the negotiation fails. The browser's mitigation protocol is immediate. It blocks the connection and destroys your pending payload before it touches the network. Your JavaScript promise is forcibly rejected. The application logic remains isolated from the network layer. That red CORS console error is simply the terminal output of this failed pre-flight negotiation. It means the browser did its job. This side-by-side waterfall chart shows the macroscopic execution timelines of the two request types. The physical system design cost of this security becomes obvious. A pre-flighted request doubles the network round-trip latency. Every API call requires an extra round trip just to ask for permission. In production, this overhead penalizes your performance budgets and degrades core web vitals. To mitigate this latency, system architects implement an optimization, caching the pre-flight. When the server responds to the initial options probe, it can issue an access control max age header alongside its permissions. This header instructs the browser to remember the permissions for a set number of seconds, skipping the options probe for identical future requests to that endpoint. With the cache active, your complex, pre-flighted requests execute with the exact same speed as a simple request. The CORS pre-flight is a security handshake. It enforces the web's baseline isolation boundary while giving developers the tools required to build complex, distributed networks. If you've spent any time writing front-end code, you've hit this roadblock, the red CORS policy error in your browser console. It looks like a bug, but it is actually a deliberate security feature. This restriction is called the same origin policy. Your browser acts as a strict bodyguard, preventing malicious websites from silently requesting data from authenticated sessions on other sites. Picture a standard setup. You have a front-end web application on one domain, attempting to fetch user data from a backend API located on an entirely different domain. Because these two origins differ, the browser requires them to successfully negotiate mutual trust before it allows any data to be read. That negotiation happens entirely through CORS headers. Let's trace a simple GET request. When your code makes the call, the browser automatically slaps an origin label onto the outgoing request to identify exactly where it came from. Your front-end JavaScript cannot forge or alter this origin header. The browser strictly controls it to ensure the destination server knows the true source. The request arrives at the backend. The server reads the origin header and checks it against its internal VIP list of approved domains. If the domain is approved, the server explicitly grants permission by stamping the response with the exact string access control allow origin. Upon receiving the response, the browser checks for that specific permission stamp. Once verified, it clears the block and hands the data payload over to your front-end code. That infamous CORS error happens when the server fails to provide the correct permission stamp. The browser receives the data, but steps in to hide the response to protect the user. Let's look at a high-risk scenario. Your application makes a post request that includes a secure custom authorization token. Because this operation can change state on the server, the browser halts the main payload. Instead, it sends an invisible scout across the network, an options request, to ask for permission first. This is the pre-flight. The pre-flight scout carries a specific query, access control request method. It is asking the server if a post action is acceptable. The server replies with an access control allow methods header, providing a checklist of the actions it accepts. Based on this pattern, think about the custom authorization header we attach to the main request. What response header must the server send to approve it? The server must explicitly return an access control allow headers header that includes authorization. Complex requests require this explicit, invisible handshake before any actual data moves. It guarantees backend systems are protected from unauthorized actions. With all permissions officially granted by the pre-flight, the browser finally releases the actual post request and safely completes the data transfer. When you need to diagnose a CORS issue, stop guessing. systematically map the browser's request headers against the server's response headers. This matrix shows exactly what to check. On the request side, the browser locks in the origin and the access control request method. You cannot forge these. On the response side, the server must mirror those requests with its configuration, allow origin, allow methods, and allow headers. By treating CORS as a strict mapping of browser requests to server approvals, you replace a frustrictable, easily solvable diagnostic checklist. Modern web applications are strictly decoupled. The front-end interface and the back-end database operate as separate entities, communicating across a digital chasm. To function at all, the client has to request data from standalone microservice APIs. Suppose you are building a dashboard. You need to initiate a network request to pull the current user's private profile data from the server so you can display it on screen. Looking at this code editor, you write a standard fetch request. Because you are asking for private data, you add the credentials include flag. This instructs the browser to attach the user's session cookies, ensuring the server knows exactly who is asking. On the server side, you want to guarantee the front end can access the response. You configure the cross-origin resource sharing headers, setting the access control allow origin to the global asterisk wildcard. You are explicitly telling the server to permit access to any requester. You run the code. Instead of loading the profile, the browser forcibly terminates the connection. A massive red CORS error blocks up your console. The browser's internal security mechanics have deliberately intercepted this request, treating the specific combination of a wildcard and credentials as a hostile act. Every front-end developer has fought with CORS errors. When a request gets blocked, the immediate temptation is to bypass the friction by throwing a wildcard on the backend to get the data flowing. Placing an asterisk in an access header sends a very specific message to the network. It tells the browser that the server has enacted an absolute abdication of access control. That open door policy collides heavily with the mechanics of session cookies. When you ask the browser to send user credentials, you are introducing highly sensitive state into the pipeline. The browser does not blindly trust the server's instructions. It acts as an autonomous firewall, independently evaluating the mathematical safety of the transaction. Combining the wildcard's implicit trust with the explicit risk of user credentials creates a systemic paradox the browser refuses to compile. To see exactly why the browser rejects this, we have to look at the foundational security bedrock of the web. Browsers are inherently hostile environments, executing untrusted code from servers all over the world. This illustrates the primary defense, the same origin policy. It places an impenetrable barrier between domains, preventing data flow. An origin is defined by three components: the protocol, like HTTPS, the domain, and the port, like 443. If any element differs, the wall locks down communication. The same origin policy guarantees that a script loaded on one origin is completely blind to the data housed on another. A script running on a news site cannot read your banking tab. This creates severe architectural friction. Modern distributed web applications rely entirely on cross-domain APIs. The same origin policy is the necessary prison that keeps the internet secure, but our architecture demands a controlled method for breaking out. CORS is the standard protocol for puncturing this barrier. The browser attaches an origin header to the request, identifying it. The server evaluates this, responding with the access control allow origin header. The browser verifies the match and allows the payload across the chasm. This brings us to the actual, valid use case for the wildcard. If a server is distributing purely public, unauthenticated assets, like web fonts or weather data, the asterisk tells the browser it is safe for anyone to read the response. Public resources operate under different rules than private resources. The threat model changes completely the moment a specific user is identified. CORS operates as a strict opt-in protocol, where servers must explicitly lower their defenses for specific verified callers. To construct the exploit, we have to look at client-side state. Cookies are the mechanism the browser uses to establish and maintain your authenticated sessions. The browser performs a critical automatic behavior. It faithfully attaches your unexpired cookies to any outgoing network request, destined for that cookie's specific domain. Assume you are currently authenticated with a secure API. In another tab, you navigate to an entirely separate malicious website. That malicious site executes JavaScript in the background, firing a hidden fetch request directly at the secure API. It is attempting a cross-site request forgery. Because the browser automatically attaches your session cookies to that background request, the API receives what looks like a perfectly valid authenticated call. If the API's response includes a wildcard, the server processes the data and sends your private information straight back to the malicious origin. Without extreme browser intervention, the combination of a wildcard and automatic credentialing transforms a simple API into a massive data leakage pipeline. Now we return to the exact moment of the fetch error from our initial setup. In that scenario, the server actually received the request. It processed the credentials, executed the query, and sent the sensitive payload back over the wire. But the browser intercepts the server's response before the JavaScript engine is allowed to read a single byte. It evaluates the transaction against the W3C specification. It spots the credentials include fly. It spots the wildcard response. It registers a critical spec violation. The browser actively destroys the response payload in memory and throws the CORS error to the console. This console error represents a successful interception, effectively neutralizing a high-risk data breach before the payload ever touches the application layer. To fix this, you have to architect an API that accepts credentials securely without triggering the browser's veto. The first requirement is that the server must completely abandon the static wildcard for any authenticated route. This diagram outlines dynamic origin reflection. An incoming HTTP request arrives, carrying a specific origin header. The server must programmatically extract this origin header. Then comes the validation phase. The server compares this extracted origin against a strictly maintained whitelist of trusted domains. If validated, the server dynamically echoes that exact specific origin back in the access control allow origin header. It then adds the final mandatory header required by the browser specification to unlock the data, access control allow credentials set to true. The browser evaluates this new precise pairing of headers. It verifies the explicit trust and finally passes the JSON payload to the front-end code. Modern web security demands explicit, verified trust at every network boundary, ensuring that private data is only accessible to authorized origins. You deploy a backend configuration that dynamically returns the exact access control allow origin header required for each request. Yet in production, users encounter intermittent blocks that prevent the application from loading data. The standard response is to rewrite the backend logic, or scrutinize the front-end framework, or disable security protocols in the local development environment to bypass the error. These failures are rarely caused by a bug. They occur because browser security policies are interacting with the invisible barriers of global deployment infrastructure. Managing CORS exclusively through application logic leaves the system vulnerable to the environment it runs in. Stable production routing requires looking past the application layer. The same origin policy is a wall enforced by the browser. CORS acts as a specific negotiated loophole through that wall, but it relies on consistent communication between the client and the server. Enterprise architectures use content delivery networks to reduce latency by distributing payloads across global nodes. A CDN changes the request path. Instead of reaching the server directly, requests stop at a central intermediary. To optimize speed, these nodes cache responses by URL path, stripping away origin metadata and ignoring the security context required for a cross-origin handshake. When dynamic security policies meet these rigid caching layers, the system becomes susceptible to unpredictable failures. If user A requests a resource, the backend attaches a uniquely colored authorization tag. The CDN caches this response, storing user A's header globally. When user B requests that URL, the CDN recognizes the path and bounces back the cached packet without consulting the server. User B receives an HTTP response explicitly stating that only site.a.com is allowed to access the data. The browser detects the mismatch between site.b.com and the cached authorization header. To prevent potential data theft, it hard blocks the request. The backend logic performed correctly, but the CDN served a valid security header to the wrong user. This is the mechanism of cache defacement. The specification-compliant fix for this behavior is the HTTP vary response header. the origin server must attach vary origin to the response payload to change how the CDN handles the data. This forces the CDN to recognize the cache key includes the requesting origin. This single cache block fractures into multiple distinct compartments. Traffic from different domains is now safely routed into isolated buckets, preventing cross-contamination of CORS headers. This creates a performance trade-off. By preventing cache defacement, you reduce the cache hit rate, as the CDN must now store a separate copy of the asset for every unique requesting domain. Enforcing vary origin resolves the errors, but it forces a choice between security integrity and CDN efficiency. Resolving the caching bug does not remove the architectural friction inherent in cross-domain API calls. Browsers restrict cross-origin requests that have the potential to alter server state. This restriction triggers an options pre-flight request before the actual API call can be executed. This adds significant latency. Each interaction requires an extra round trip across the network just to verify permission to communicate. Even when pre-flight responses are cached using access control max age, the requirement remains a constant architectural drag on performance. Optimizing these headers mitigates the damage, but some architectures avoid these penalties by removing the cross-origin boundary entirely. One strategy utilized by enterprise stacks involves removing CORS from the client-server interaction entirely using a reverse proxy. This relies on the fact that the same origin policy is a browser-side mechanism. Server-to-server communication is immune to these restrictions. Implementation involves deploying routing layers, such as Nginx, Cloudflare workers, or Next.js rewrites, at the edge of the front-end deployment. The proxy maps the backend API to a subpath on the front-end's domain. The browser communicates exclusively with a single origin. When a user triggers an action, the reverse proxy intercepts this request internally and tunnels it seamlessly to the hidden backend server. Because the request URL matches the front-end domain, the browser processes it as a standard same-origin request. This removes the bottlenecks. The browser never initiates an options pre-flight, and the server never needs to generate CORS headers. Without dynamic security headers, the CDN can cache paths for all users without the risk of cache contamination. By creating a single, unified origin, reverse proxies decouple application logic from browser security constraints. Systems engineers can evaluate their routing requirements against a specific architectural decision matrix. If you are building a public-facing API for third-party domains outside of your organizational control, you must use CORS headers. In this case, enforcing vary origin is required to protect the integrity of the CDN cache. However, if your organization owns both the front-end and the back-end, exposing cross-origin endpoints to the browser introduces unnecessary complexity. Internal ecosystems should default to reverse proxy routing. Modern frameworks frequently build these proxy capabilities into their deployment defaults to simplify the path to production. Efficient CORS management in enterprise environments relies on infrastructure design. By ensuring the browser never sees a cross-origin boundary, the entire class of caching and pre-flight errors is eliminated.